Hello mathematicians, we're now going to have a look at finding area by integration for slightly more complicated situations. So as you're probably aware, we can use the definite integral to determine the area between the curve and the x-axis. But you're also aware that because of the properties that we've looked at, we need to simply do more than evaluate the definite integral. We need to do a sketch so we can see whether there are positive or negative areas involved, and then which separate integrals we might have to set up. So if we have a look at a typical question, it says sketch this cubic curve showing the x-intercepts. Now, we're only interested in the x-intercepts because we simply want to know where the curve is positive and negative. So if we sketch this up, we can see that the x-intercepts are at x equals 0, x equals minus 1, and x equals plus 2. And if we take a test point and see whether it's positive or negative, so if we took, for example, x equals 1, we'd have a positive times a negative. So at x equals 1, the curve is negative, and that's all we need to know, which way the curve dips. Then, if we look at the areas that we would be wanting to find to get the area trapped between the curve and the axis, we can see that we've got a positive area between minus 1 and 0 and a negative between 0 and 2. So to actually find the region enclosed, we need to find the area enclosed, we need to break the region up into two parts. So we're going to have an integral from minus 1 to 0 of our curve. Now this is just the curve, the expression multiplied out, because as you know we have no product rule. And then we're going to have to take the absolute value, we're missing the other line, the absolute value of the integral from 0 to 2, because we can see that it's negative on our diagram. If we then do our integration, we'll get x to the 4 on 4 minus x cubed on 3 minus x squared. And when we evaluate that integral from 0 to minus 1, when we put the zeros in, we get 0. When we put minus 1 in, this is what we get, which comes out to be a negative 5 on 12, and the minus makes it a plus 5 on 12. For the area under the curve, obviously the primitive is the same, and our limits are 0 and 2. When we put the 2 in, we get this, which is a negative. When we put the 0 in, we get that. So this is negative 8 on 3. We'll take the absolute value of that to get plus 8 on 3. So altogether, our area is 37 on 12. Now we can also use the definite integral to find the area between a curve and the y-axis. So to do this, what we have to do is to write the function as f of y. So we need to make x the subject of the equation. And our limits of integration become the y values on the axis. And then we use the definite integral a to b f of y dy. So you'll notice that around, or with respect to the y-axis, it's dy, and we remember that f of y means you make x the subject of the equation. So if you like, y becomes the variable. So if we look at this in practice, to sketch this cubic over this domain, and then to find the areas of the shaded regions. So this is our cubic sketched up. We can see that we have uneven areas. We want this area here, which will be positive, and this area here, which will be negative. So if we just skip to part B, find the total area of the two shaded regions, our expression will be the integral from 0 to 8, so when x equals 2, y equals 8, and the equation with x as a subject is the cube root of y, and we're integrating with respect to the y-axis. And that first part will be positive. Our second part, from y equals minus 1 up to y equals 0 of our function, is going to be negative, so we take the absolute values when we integrate with respect to the y-axis. So we find our primitive, which will be the same in both cases. When we substitute our values in, 8 and 0, we get a 12 minus a 0. And when we substitute our values of 0 and minus 1 in, we get 0 minus 3/4. That's why we're taking the absolute value. So together, our total area is 12 3/4. And then we could try these questions in 11E.